Hey ANPers, this is Dr. Jones checking in. This is ANP1, Lecture Test 5, Video 17, covering page 18. And this is the end of Chapter 12, the last page of the Chapter 12 note set. First, and this isn't on the note set, but we will come across this next semester. So I want to put this idea in your heads. I'm not going to test you over this until next semester, 2402. But I kind of just want to seed the idea in your mind that this happens so that when you see it, it won't be completely new and it won't flummox you that there's something new happening. So there are a number of ways that neurotransmitters can work. We have direct effects, and this is what we've been talking about with chemically gated in this case, sodium ion channels, where the chemical binds to the receptor, which opens the channel, and then the ions can cross the membrane. And so these are the direct effects with chemically gated ion channels that we're talking about this semester. Next semester, next semester, you will see this happen, the indirect effects with G proteins. So what happens? The neurotransmitter binds to the receptor, and the receptor without the neurotransmitter has an inactive G protein. When the neurotransmitter binds, that activates the G protein. And then that G protein, and there's a number of different ways the G protein can work and what it can do, but it activates an enzyme that breaks down an ATP that causes an ion channel somewhere else in the cell membrane to open. So these are called indirect effects. There's at least 3 different ways that they work, picture later in the book. But they all have the G protein in common. Some of them use cyclic AMP, some of them use calcium. Next semester. Just so you know, this can happen. And then this activation of an enzyme can open an ion channel. We won't specifically, or at least I won't specifically talk about in 2402. Some of the other instructors might. But it's not directly relevant to what I talk about. So you know, this indirect thing with the G proteins happens, and that is epinephrine and norepinephrine. We are talking about that, but not to this degree. So you know. All right. So page 18. Some stimuli are excitatory. Sorry, just get that out of my way. Which means depolarizing. So here you start at your resting membrane potential, which is negative 70 millivolts. And an excitatory stimuli is depolarizing. It makes the inside of the cell less negative compared to the outside of the cell because positive ions have rushed in. Tiny bit of an oversimplification, but we're totally going with it because that's all we need to know for now. And some are inhibitory. So a sodium ion channel would be depolarizing. My Z's are actually neater in cursive. That's so weird. And depolarizing, which is excitatory. A-T-O-R-Y. Here we go. Excitatory, because it brings it closer to threshold. So depolarizing is closer to threshold, so that makes it easier to make an action potential, so that's excitatory. Okay. If, however, I guess we could switch to blue here. Let's do cyan so it shows against the blue in the picture. If, however, you activate a potassium ion channel, then it's hyperpolarizing. If I go slow and think about it, I can make my Z's almost legible. I cross my Z's so that they look different than my 7s, which I also cross. Yeah, that doesn't really work anyway. Okay, so these are inhibitory. It's as we've discussed before with a hyperpolarizing part at the end of the action potential, it takes you literally further from threshold. So instead, so here you're 20 millivolts away from threshold. At, we'll do a blue resting. At resting, you're 10 millivolts away. And, come on, I want a different color. There we go. So here, let's say it goes halfway. Here, let's say you're 5 millivolts from threshold. So this is, anytime you open a sodium ion channel, it's going to be excitatory because it takes you closer to threshold. Anytime you open a potassium ion channel, it's going to be inhibitory because it takes you further from threshold. Actually, if that went up 5, this went down 5, and then that's 15. 15. It's a 5. How is that a 5? I apologize for my terrible handwriting. To be fair, if we were in person and I was writing on the board, it would be actually worse because this is my bum shoulder and writing on the board, it gets tired. It doesn't work well. Okay, so some stimuli are excitatory. We're still top of page 18, aren't we? Which is depolarizing, and some are inhibitory, which is hyperpolarizing. Excitatory stimuli bring the membrane closer to threshold and are there's a word that's supposed to go there. Excitatory stimuli bring the membrane closer to threshold and are depolarizing, excitatory. Kind of already covered all of that. Inhibitory stimuli push, sodium ion channels? I don't remember what I had there. I don't have it on my other version. Inhibitory stimuli push the membrane further from threshold and are hyperpolarizing, which I think we've already said. Therefore, excitatory stimuli make the creation of an action potential more likely, while inhibitory stimuli make the action potential less likely. The net effect of all of these stimuli on the axon hillock determines whether or not an action potential will be propagated at the initial segment. Because as you may recall, it's whether or not you bring the whether or not you bring the initial segment of the axon to threshold that decides whether or not you make an action potential. In fact, this is what we're talking about when we say information processing. Like literally, has there been a big enough message to make an action potential? Like, have you had enough graded depolarizations to bring the initial segment of the axon to threshold? And that's your information processing right there. It's all about the ions. Don't worry, next semester we get into the heart and the lungs and we'll like squeeze stuff and it'll move. It's more complicated and simpler at the same time. Oh, okay, and this is called information processing. Back to the note set. Information processing is the next fill in the blank. Okay, postsynaptic potentials are graded potentials. Excitatory postsynaptic potentials are depolarizing, and they're abbreviated. That was supposed to be read EPSPs. Excitatory postsynaptic potentials. Those are depolarizing graded potentials, which they've just given an even longer name with a bizarre set of initials for us to remember. Thanks. Great. I'm so excited. I'm sure you are too. Is what it is. Okay, so the inhibitory postsynaptic potentials are hyperpolarizing graded potentials. So EPSPs are depolarizing, while IPSPs are hyperpolarizing. Okay, and then draw this picture right here, this picture. And here's the thing I want you to make sure you get down. An EPSP and an IPSP that happen at the same time cancel each other out. Here's our potential. It goes down, it goes back. EPSP and IPSP at the same time, nothing happened. Okay? It's like if you buy a $10 Kohl's shirt and pay $10 on your Kohl's card at the same time, nothing happened. You're still $70 in debt. So the EPSPs and IPSPs can cancel each other out. Did I say that 5 times yet? Okay, next. Oh, no, not yet. Oh, yeah. Okay, sorry, I got lost in my pictures. Summation is when you add the effects of the graded potential. A sum is the answer of an addition problem, like 2 plus 3 equals 5. 5 is the sum. The 2 and the 3 are called add-ins.